feel free to add or expand on anything that you wrote in your survey. So just hold on to your surveys. And I'm just going to start off with my little self-introduction. And so my passion is for making the concepts of higher math understandable and interesting to students. And so I actually, also I'm a textbook author. So back 1989, I think it was 1988, I was published a calculus textbook. So I'm a co-author of a calculus textbook that helped me pay my way through graduate school. And then I wanted to try to get my own TV show. So I know Bill Nye the Science Guy, and the way you get your own TV shows, you have to create your own little video vignette snippet to catch their interest. So I did create some things. I hired a professional videographer to work with me, but unfortunately they told me they weren't interested. But I will show you one of the ones I created. It's just 5 minutes long. It's called The Mathematics of Hamburger. So what's going on here is when a hamburger leaves the grill, you have to cook a hamburger to 160 degrees to kill off all the bacteria. That's the general kind of rule. When you heat up meats, you want to heat up to 160 degrees. And then the moment that the hamburger leaves the grill, it begins cooling, and the equation that describes the cooling obeys what's called Newton's law of cooling. So Newton's law of cooling says the rate of change of the cooling is proportional to the difference in the temperature between the hamburger and then the surrounding air. So the bigger that difference in temperature, the faster the cooling, and then the cooling becomes slower and slower as the temperatures get closer together. So you experience this directly when you go to the amusement park and you ride one of those rides where it's like a water ride, you get all wet, and then you begin to dry off, and the rate at which you're drying off depends on the humidity of the surrounding air. So initially you start drying off very quickly, but then as your clothes begin to dry off, they still stay damp for quite a bit of time, because that difference between the humidity, the dampness of your clothes, and then the dryness of the surrounding air, that becomes closer and closer together. So the rate changes. So that's what I described here. These are made for middle school students. And so I used to have a school called Dr. Frank's Bushiban School, which is an after-school school. In fact, this is a picture of me at my school, Dr. Frank's Bushiban School. This girl over here graduated from OSSM in 2011, and later went on to Harvard, and now is working for, I think, Twitter at this time. So she was just here at our reunion, but I couldn't recognize her because she changed so much. I'm not sure when this picture was taken, probably like 2003 or 2004. So funny thing about when I call it Bushiban School, a Taekwondo business threatened to sue me because they called me up and they said I stole their name because it was I don't know anything about Taekwondo, but there's a Taekwondo called Bando, and there's another one called Bushi, and then he created this combination of the Bushi and the Bando types of Taekwondo, so it was a Bushi Bando Taekwondo, and he said that I stole this Bushiban name from him, and I told him, I said, no, I said in Chinese, Bushiban means like an after-school school, so I said it's nothing to do with Taekwondo, so we worked it out, and I didn't get sued. So here we go. It's about 5 minutes long.
Oh, I'm sorry, I forgot. It's time for Dr. Frank's Math Minute.
And my wife was the one that drew the little cartoony figure.
But even more importantly, it's time for lunch. Let's head off and get ourselves a nice juicy burger.
And this is about 10 a.m. in the morning, so they didn't close the restaurant for us.
A burger has to be heated to at least 160 degrees to ensure that all the bacteria is killed off. Besides, there's nothing tastier than a piping hot burger, as Zach is cooking here behind me. Thank you. From the moment the hamburger leaves the grill, it begins cooling. In fact, the process of its cooling and its temperature is governed by what's called Newton's law of cooling.
Is there anything else I could get you?
Well, in fact, yes. I would like a digital thermometer.
Sure.
Oh, wonderful. Just what I was looking for. A marker and specially marked graph paper with its temperature measured in degrees Fahrenheit along the vertical axis and time marked in minutes along the horizontal axis. Oh, perfect. You are the waitress
the
who got
graph paper
perfect.
with the little grid lines here, so I had to
Oh.
wing it a little bit.
Since I can't eat this juicy hamburger, could I have a plate of pickles, please?
And then a pickle bar where you
Oh,
can eat
wonderful. This should
unlimited
come
pickles.
lastly for the whole experiment. Newton's law of cooling is described by what is called a differential equation. A differential equation is a special type of equation that involves the rate of change. Let's review quickly. Here, let's suppose we have the temperature function. A function, as you recall, is a machine that takes in numbers as inputs. For example, the numbers might represent the time. I put in number 3 here, and has outputs. In this case, the outputs are the temperatures. So this would indicate that at t equals to 3 minutes, after 3 minutes, the burger is cooled to a temperature of 155 degrees. And so the differential equation relates t, the temperature function, and t prime, which is the derivative of the temperature function. And so this equation that relates the temperature and its derivative, which is itself a function, is the differential equation that we call Newton's law of cooling. Newton's law of cooling states that the rate of change of the temperature is proportional to the difference of the temperature of the burger and the ambient temperature. That is, the greater the difference between the temperature of the burger and the surrounding air, the faster that it will cool. Solving the differential equation means finding an explicit expression for the function t. We'll show the solution here rather than go through the nitty-gritty of actually solving the equation. We'll take this explicit expression for t, and then we're conducting an experiment and compare the experimental result with the theoretical result. Let's begin our experiment.
So these are not picked up numbers. I was actually measuring the temperature using the meat thermometer and then a little watch. But the chart I was using didn't have the grid lines. I got the wrong paper, so I had to kind of eyeball where the data points were. And the pickles, I'm not actually eating them. I'm just throwing them into a bowl next to me. I think we went back and used a computer to actually plot out the data points later. So.
Boy, am I glad that that experiment's over. I can't wait to bite into that juicy burger. Well, instead I ate a whole plate full of pickles. Let's take a moment now and compare our experimental results with the theoretical results.
So it's actually pretty good. It's pretty good. When we plotted the actual data points, experimental compared to theoretical, it was very close.
Before the burger gets any cooler, I better take a bite. Oh.
Okay, so what happened was I made a few of these. I got another one. You won't watch the whole thing. I'll show you just the beginning. This one was, I think the first one we created was the, I was at the St. Louis Arch, and we want to estimate the height of the St. Louis Arch using similar triangles.
I'm now speaking to you from St. Louis with the arch behind me, and the problem we are now facing is how to measure the height of the arch if we did not already know it. We actually know that it is a distance of 630 feet from the very top of the arch to the ground. But assuming we did not know that, what method would we have for finding the height? Well, we're going to use a yardstick here, some measuring tape, and the principle of similar triangles. We believe.
So what happened was, the videographer said, let's script the whole thing out and then we'll make the numbers work out, blah, blah, blah. And I said, no, that felt to me to be intellectually dishonest. I said, let's just do it for real. I said, let's just do it for real and then see how it turns out. So we did it. We just used the yardstick. We measured the shadow at the length of the yardstick. And then I paced out at 3 feet per pace, the distance from the end of the shadow to the bottom of the arch. And we actually came up with within about 5% error. But anyhow, we took the videos, we patched it up, we sent it off to, Bill Nye, the Science Guys producers. And they basically just came back and said, no thanks. And they explained to me, they said, look, Dr. Wong, they said, TV is a very visual medium, and we want stuff that's really visual. And they said that in science, scientists blow up things, and people like to watch that. And they said also, there's a chance that someone could get hurt, and people like that too. And they said that in your videos, nobody's gonna get hurt, and maybe the worst thing that's gonna happen is someone gets a headache. So they just said, thanks, but no thanks. And that's why I'm teaching here at OSSM right now, because if my show had taken off, you would be watching me on TV as Dr. Frank, the math guy. I didn't want to say Dr. Wong, the math guy, because people don't know how to spell Wong, W-O-N-G or W-A-N-G, and so we decided to use, we decided to use Dr. Frank. So, okay, and just to let you know, oh yeah, so my passion is for making the concepts of higher math accessible and interesting to students of all ages. So I actually started my own little company called Wong Education. And this is a product I created called Group Theory with Fruits, where I teach the principles of group theory, but using fruits as a group element. And I even had a DVD, this is back in the early 2000s, a little DVD kit. And then I had, people would do multiplication, they would actually do algebra using the fruits. Like you would fill out multiplication tables with the fruits, and then you would have calculations you would do using the fruits. Anyhow, I personally thought it was like a really ingenious thing, because I thought when I was taking abstract algebra at Princeton, so it says like simplify apple times cantaloupe times bananium. Anyhow, I invented this whole thing, and I even taught it on live cable TV back in the later 1980s. And I have a tape of that. Anyhow, so I was thinking to myself, I said that I would create this business to share the power and the beauty of higher math. But it was a total failure. No one wanted to buy anything. This is sold for like $49.95. And my wife was making fun of me and said, there's no money in math enrichment. You got to do math remediation. Then I was actually at a teacher's conference selling this program, and a teacher ran up to me and said, I'm part of a really dysfunctional math department and no one talks to each other. I heard you have a group therapy program. And so I said, no, it's not group therapy, it's group theory. They thought it was like where each person holds a fruit and talks to each other, because when you do therapy, sometimes you put the hand puppets on, and then like you can't say something to somebody else that you really want to say, so the puppet says it. Have you seen that before, like the therapy with the puppets, and the puppet says what you really think, and the puppets talk to each other. Anyhow, they thought it was something like that. So what happened was I had to just shut down the whole business. I ended up just spending a lot of money. I think I probably spent like more than $100,000 creating this stuff, and nobody wanted it. So I was a total failure, and so basically that's why I'm here teaching at the Oklahoma School of Science. No, that's a little bit oversimplified, but my passion is for teaching. I want to share a little bit of background on myself, but to really kind of explain why I'm so passionate about teaching. And then I'm going to begin with a doctor's report. And it says, in review, I feel we're dealing with a child who has neurological impairment based on the history, delayed milestones, and minimal suggested neurological signs. The top paragraph talks about my mother. It says, I explained to the mother what I felt about his delayed milestones. As he walked at 16 months, so I couldn't sit up at 8 months. He said, after I told her all this, I really feel I didn't get through to it all. She still feels he's not a problem, is progressing well, and the school is of little difficulty to him, except he's a little behind. And the school actually wrote a letter to my parents. This is dated December 8th, 1970. I was born in September 1964, so I was 6 years old at the time. It says, "Dear Dr. and Mrs. Wong, we have received Dr. Seth Ducati's neurological report. A copy of this report has been sent to Dr. Schobel, your physician. Would both of you please make an appointment with my office to discuss the educational implications of this report?" So this is basically what happens. I'm in elementary school, I'm in first grade, kindergarten, first grade at the time, and the teacher contacts the principal and says, "I think we have a severely learning disabled child in our class." And so back in the 1950s and the 1960s, early 1970s, the prevailing thought was if you had a child who had severe disabilities, whether it be physical disabilities or mental disabilities, you sent them to a special school. They just felt like that it would be better to educate the kids in a separate setting. Now that's totally changed. The whole society's changed. The basic feeling now is we need to be as inclusive as possible. So if you have a physical or mental disabilities, we want you to be with other students as much as possible. We want you to be part of the broader community. But at the time, the principal met with my parents and just basically said, "I'm very sorry to tell you, but your son has no academic potential. He's just not, it's a waste of time to come to school. He doesn't have the ability to learn," because it says very clearly that I had neurological impairment. And I still remember as a child being taken to the hospital or the doctor's office, and they said you had to sit very still. It was hard for me to sit still. And then they put notes on my head. They hooked me up to the machines, and they basically said, "We see very little brain activity." That was the basic conclusion. So what happened was, but my parents protested. And they said, "No way." They said, "We're not sending our kids to a special school." And they also wanted to give me drugs to stimulate my brain. They said, "We don't want to give them any drugs or anything like that." So they insisted on keeping me in school. And so what happened was I pretty much fulfilled the prophecy that was made of me. And I always got sat at the back of the class. I didn't know why because I was a kid. But I realized what happened was the teacher would just look past me and just kind of say, "Oh, there's that Chinese kid whose parents are too stubborn to realize that he doesn't belong here." So I got socially promoted. Socially promoted means every year they just kicked me to the next grade, the next grade, the next grade. And basically the only thing I ever learned in elementary school was that if you turn on your oven and you press your forehead to the oven, you could make your forehead really hot. And I hated to go to school, so I always went to my mother and said, "Mom, I don't feel well today. I feel kind of sick." And she would feel my forehead and go, "Oh my gosh, you have a fever. You need to stay home." And so I missed a lot of school because I just was pretending to be sick. So finally I got to junior high school and something snapped at me. I don't know what it was. And I wanted to prove to the world I was smart. I was like, I'm sick and tired of everybody's treating me like I'm just a total dummy, and they wouldn't, they just had no expectations for me whatsoever, and I was just ignored. And and I didn't have very many friends. I was just basically just some kid that the teachers, the administrators, and other kids just kind of wrote off as someone that didn't belong there. So I noticed this one thing. I noticed that I went to school in New York, that if you were considered smart, you got to take algebra in junior high school. I just noticed that. I said, and if you were considered normal, you took algebra in 9th grade in high school. I was in what they call junior high school. And if they considered you to be hopeless, they just stuck you in consumer math, and they didn't even try to teach you algebra. So in New York State, they had a truth in testing law that says any high stakes exam has to be made public. So Barron's would print the old Regents test in cheap newsprint. So I got a hold of these old Regents books and I started memorizing the answers. And I really didn't know what I was doing. I had no clue. I just started memorizing the answers and just memorizing a lot of things. So the first day of school comes along, I'm in junior high school, I walk up to the algebra teacher and said, "Mr. Algebra teacher, I think I already know algebra." So he looked at me with amusement because he thought, well, this is a kid that has no potential. But to his credit, he sends me down to the principal's office, and the principal sits me down. All the principals have these little round table in their office. I said, "Frank, let me see how much algebra you know." And back in the old days, they didn't have Scantrons. Like the technology was very basic. But all they did was you take this multiple choice test and fill in the bubbles, but they had a piece of cardstock with holes in it, and you could overlay the piece of cardstock with holes over the kids' test answers, and then you could kind of see which ones they did wrong. Sometimes they said they would take a marker and run it through where the holes were, and you could kind of see where the mistakes, you could grade really fast. It was a low-tech version of the Scantron. So principal said, well, Frank, let me give you a Regents test and see how much you know. So he goes to his office, grabs the old Regents test and throws and says, here, take this. But I had already seen the answers to the test, but I didn't say anything, you know. So I take the test, and then in one of the most delicious moments of my life, he grades the test, and I scored like a 96. I only missed like 2 out of 50 questions. And he looked at me and said, Frank, he goes, where did you learn algebra? And I said, I don't know, it just came to me. And so I told like a bald-faced lie, you know, and so he, at that point, my whole situation was reevaluated. They said, man, they said, you know, we've been mistreating this kid. He's been a genius all along, and we just didn't even know it. They said, maybe when we stuck the nose on his head at the neurologist's office, we reversed the polarity, and it came out really negative when it should be come out really positive, you know. So anyhow, I made up the whole thing, you know, but overnight, people started treating me differently. It's like when you read the paper, they say person freed from jail after 25 years because they tested the DNA at the crime scene. They found out the guy's DNA wasn't there. It was a mistaken identity. So same thing for me. They said, wow, they said Frank Wong is really a genius, and we've been mistreating him. So overnight, I started being treated like I had a lot of potential. And at that point, I had an epiphany. You know, I kind of thought to myself, I said, you know, in this world, there are kids that are treated like they have no potential. Their whole life, they're just treated like they're nothings. And then, on the other hand, you've got some kids that are treated like they have tremendous potential. And everyone pours a lot of energy and love into them, you know. And so, like, even when my kids were born, when my wife was pregnant, she was pumping in Mozart into the fetus thing. We can make him smarter by listening to classical music, you know, it's all this made up stuff. Anyhow, so, and I vowed to myself, I said, someday if I ever become successful and I make some money, I'm gonna make it my life's mission and passion to preach the message that each and every child has tremendous untapped potential. So I spent a few years traveling around the whole country, giving talks to teachers. I've spoken to more than 30,000 teachers around the whole country. And so I had a chance to take a company. I met a guy when I was your age. Back in 1980, and then he passed away in 96, but he started his own textbook publishing company, and I ended up growing it to about 100 million in sales. So in my 30s, I made enough money to retire. I didn't have to work anymore. So I really had a passion for teaching, but I didn't have a teaching certificate. So I came to teach at OSSM in 2003, 4, and 5 for free. So I took no pay when I was teaching here before. When I was in college, I co-authored a textbook. So this is a textbook that I co-authored, and I used that money to help pay my way through graduate school. But one thing I want to tell you, all of you guys are a lot smarter than me. So I just want to tell you that when I'm teaching you, at some points, I'm going to get totally confused and befuddled. And you're going to think that I'm, you know, making it up, or so I'm just trying to test you. But the truth is I get confused very easily. To this day, I don't know how to tie my shoelaces. It's very hard for me to figure out the tacks when I go out to eat. And people will think, you're making it up. You can do it all in your head. And that's totally not true. I have math is extremely difficult for me because, you know, the next day they stuck me in geometry, and I had basically no education up to that point. You know, I was faking it the whole time, pretending I was sick, but then I wanted to pretend I was smart. But I was one of those cases, and this is a super bad analogy, but it's like someone that maybe has an eating disorder or suffers from anorexia or something, that I couldn't stop because I just was so driven to prove the experts wrong. I ended up getting a PhD in pure math from MIT, not because I really have any ability in math, or not even because I like math. I was just so driven to prove the experts wrong. I want to tell you kind of a funny story, is I went around the whole country giving talks, and this guy, Dominic Ducati, I looked him up on the internet, and see, he wrote his diagnosis of me in 1970, and like in the 2000s, I was giving a talk. He practices in Schenectady, New York. I was giving a talk in Saratoga Springs, New York, about 20 minutes from his office, and I figured he was probably in his 70s. He diagnosed me in his 30s. So 40 years later, he has no idea what has become of me. And before I was going to get to the airport to fly back to Oklahoma, I wanted to go to his office and confront him face to face and say, hey buddy, you're the guy that diagnosed me as having neurological impairment. But I was super scared and chickened out because someone once told me, never make someone whose last name ends in a vowel mad. And so I figured that he would be so upset he would chop me up to little pieces and bury me in his backyard. So to this day, he has no idea what has become of me. But it's a kind of, and I told this story. It's been, you can look it up. It's on the internet, and so I've been. It's been in the national papers and stuff like that. So it's not made up. I have all the documentation to show that. So that's kind of what my. That's why my mission in life is to help kids succeed in math. You know, that's why I run you see me running review sessions at night. That's not part of my job description. They don't say, Dr. Ron, you have to run review sessions for these kids. I do it because I just have this great passion for helping young people succeed. Because I know myself, I can guarantee you, if my parents had taken the recommendation of the doctors, stuck me in the special school, drugged me up with all the stuff they wanted to give me, there is no way I would be standing here before you today. There's no way. I would be sweeping the floor someplace. I would just be totally in some dead end place. So it's, you know, I preach the message that each and every young person has tremendous untapped potential, far beyond their teachers, their parents, or even their own expectations. It's really amazing what you guys can do. So, okay, I'm going to get off my soapbox there. And so that's why we're going to jump right into lecture 1 and talk about the greatest mathematical problem of all time. The greatest mathematical problem of all time. So I'm going to play a little video here.
Perhaps I could best describe my experience of doing mathematics in terms of entering a dark mansion. One goes into the first room and it's dark, completely dark. One stumbles around, bumping into the furniture. And gradually you learn where each piece of furniture is. And finally, after 6 months or so, you find the light switch, you turn it on, and suddenly it's all illuminated. You can see exactly where you were. At the beginning of September, I was sitting here at this desk when suddenly, totally unexpectedly, I had this incredible revelation. It was the most important moment of my working life. Nothing I ever do again will.
This is about the campus of Princeton University. And he was a professor when I was there. Now he's at Oxford University.
This is the story of one man's obsession with the world's greatest mathematical problem. For 7 years, Professor Andrew Wiles worked in complete secrecy, creating the calculation of the century. It was a calculation which brought him fame and regret.
So I came to this, I was a 10-year-old, and one day I happened to be looking at my local public library, and I found a book on math, and it told a bit about the history of this problem, that someone had resolved this problem 300 years ago. But no one had ever seen the proof. No one knew if there was a proof. And people ever since had looked for the proof. And here was a problem that I, a 10-year-old, could understand, that none of the great mathematicians in the past had been able to resolve. And from that moment, of course, I just tried to solve it myself. It was such a challenge, such a beautiful problem. This problem was Fermat's last theorem.
Pierre de Fermat was a 17th century French mathematician who made some of the greatest breakthroughs in the history of numbers. His inspiration came from studying the Arithmetica, an ancient Greek text.
Fermat owned a copy of this book, which is a book about numbers with lots of problems, which presumably Fermat tried to solve. He studied it, he wrote notes in the margins.
Fermat's original notes were lost, but they can still be read in a book published by his son. It was one of these notes that was Fermat's greatest legacy.
And this is the fantastic observation of Master Pierre de Fermat, which caused all the trouble. Cubem autem indubus cubus.
This tiny note is the world's hardest mathematical problem. It's been unsolved for centuries, yet it begins with an equation so simple that children know it off by heart.
The square of the hypotenuse is equal to the sum of the squares of the other two sides.
Yeah, well, that's Pythagoras' theorem, isn't it? That's what we all did at school. So, Pythagoras' theorem, the clever thing about it is that it tells us when three numbers are the sides of a rectangle triangle. That happens just when x squared plus y squared equals z squared.
X squared plus y squared equals z squared. And you can ask, well, what are the whole number solutions of this equation? Quickly find there's a solution. 3 squared plus 4 squared equals 5 squared. Another one is 5 squared plus 12 squared is 13 squared.
So just a quick note is a little technical thing. He meant to say positive integer solutions, So we're talking about, so Pythagorean triple is a triplet of positive integer solutions to x squared plus y squared is equal to z squared. So 3, 4, 5 is a Pythagorean triple, 5, 12, 13 is a Pythagorean triple. And Fermat's last theorem states that there are no positive integer solutions to x to the n plus y to the n is equal to z to the n, where n is a integer greater than 2. So x squared plus y squared is equal to z squared has no positive integer solution. So there's no x, y, and z that are positive numbers. No positive integer solutions when n is an integer greater than 2. He says whole numbers, so it's a little tricky because whole numbers include 0. So you can say 0 plus 0 squared, 0 to the third plus 0 to the third is equal to 0 to the third. So there's like a trivial solution. So really, if you want to be technically correct, you have to say that x to the n plus y to the n is equal to z to the n has no positive integer solutions when n is greater than 2. So it's just a technical little thing here.
And you go on looking and you find more and more. So then the natural question is, question Fermat raised, supposing you change from squares, supposing you replace the 2 by 3, by 4, by 5, by 6, by any whole number n. And Fermat said simply that you'll never find any solutions. However far you look, you'll never find a solution.
You will never find numbers that fit this equation if n is greater than 2. That's what Fermat said, and what's more, he said he could prove it. In a moment of brilliance, he scribbled the following mysterious note.
Written in Latin, he says he has a truly wonderful proof, demonstrationem mirabilem, of this fact. And then the last words are, hanc marginis exiguatis non cavet. This margin is too small to contain it.
So Fermat said he had a proof, but he never said what it was.
Fermat made lots of margin notes. People took them as challenges, and over the centuries, every single one of them has been disposed of, and the last one to be disposed of is this one. That's why it's called the last theorem.
Rediscovering Fermat's proof became the ultimate challenge, a challenge which would baffle mathematicians for the next 300 years.
Gauss, the greatest mathematician in the world.
Oh yeah, Galois.
Comma, of course,
Well, in the 18th century, Euler didn't prove it.
Well, you know, there's only been the one woman, really. It's
Sophie Germain.
No, there are millions of there are lots of people. But nobody had any idea where to start.
Well, mathematicians just love a challenge. And this particular problem just looks so simple. It just
One thing to note, that someone as a joke in the New York subway wrote, x to the n plus y to the n equals z to the n has no positive integer solutions for n integer greater than 2. I have a truly wonderful proof of this proposition, but my train came. And so just made a little joke of that. But Fermat wrote this in his margin. He said, I have a truly wonderful proof of this, but the margin's too small to contain it. So we now theorize that he's made some very simple-minded mistake, because there's other mistakes that he had made. And then actually my 7th grade teacher introduced this to me when I was in 7th grade back in 1976. And said, I'll give $100 to anyone that could find positive integers that can satisfy this equation, x to the n plus y to the n equals z to the n, where n is an integer greater than 2. So I just spent all night just randomly plugging in numbers in and stuff like that. But I had no idea that this problem was so famous and that he was at no danger of losing his $100.
It looked as if it had to have a solution. And of course, it's very special because Fermat said he had a solution.
Mathematicians had to prove that no numbers fitted this equation. But with the advent of computers, couldn't they check each number one by one and show that none of them fitted?
Well, how many numbers are to be dealt with? You've got to do it for infinitely many numbers. So after you've done it for one, how much closer have you got? Well, there's still infinitely many left. After you've done it for 1,000 numbers, how much closer have you got? Well, there's still infinitely many left. After you've done it for 1,000,000, well, there's still infinitely many left. In fact, you haven't done very many, have you?
A computer can never check every number. Instead, what's needed is a mathematical proof.
A mathematician is not happy until the proof is complete and considered complete by the standards of mathematics.
In mathematics, there's the concept of proving something, of knowing it with absolute certainty.
Which, well, it's called rigorous proof.
Well, a rigorous proof is a series of arguments
based on logical deductions,
which just build one upon another.
Step by step.
And soon you get to
a complete proof.
That's what mathematics is about.
A proof is a sort of reason. It explains why no numbers fit the equation without having to check every number. After centuries of failing to find a proof, mathematicians began to abandon Fermat in favor of more serious maths. In the 70s, Fermat was no longer in fashion. At the same time, Andrew Wiles was just beginning his career as a mathematician. He went to Cambridge as a research student under the supervision of Professor John Coates.
I've been very fortunate to have Andrew as a student, and even as a research student, he was a wonderful person to work with. He had very deep ideas then, and it was always clear he was a mathematician who would do great things.
But not with Fermat. Everyone thought Fermat's last theorem was impossible. So Professor Coates encouraged Andrew to forget his childhood dream and work on more mainstream maths.
The problem with working on Fermat is that you could spend years getting nothing. So when I went to Cambridge, my advisor, John Coates, was working on the Iwasawa theory of elliptic curves, and I started working with him.
Elliptic curves were the in thing to study, but perversely, elliptic curves are neither ellipses nor curves.
You may not have heard of elliptic curves, but they're extremely important.
Okay, so what's an elliptic curve?
Elliptic curves, they're not ellipses. They're cubic curves whose solution have a shape
looks like a donut.
It looks so simple, yet the complexity, especially arithmetic complexity, is immense.
Every point on the donut is the solution to an equation. Andrew Wiles now studied these elliptic equations and set aside his dream. What he didn't realize was that on the other side of the world, elliptic curves and Fermat's last theorem were becoming inextricably linked.
I entered the University of Tokyo in 1949, and that was 4 years after.
Okay, so what they mentioned is that that solving of Math's last theorem is tied very closely to the study of what's called elliptic curves, the study of elliptic functions. I'm going to give you a little bit of description of what that is about in a very kind of basic way. So I'm going to oversimplify things. So let's look at let's just look at the sine function. We'll look at y is equal to sine x. Okay, we graph it out. And we see the sine function is periodic. It's periodic. So every 2 pi, it kind of repeats itself. So you notice, hey, if I want to understand the sine function, all I really need to do is understand what happens between 0 and 2 pi, 0 and 2 pi. So actually, after you get past 2 pi, it kind of repeats itself. So I can kind of think of taking this little line segment from 0 to 2 pi and gluing the ends together. So I take the 0 and the 2 pi glued together and I get a circle. So I can kind of think of it as that sine is a function defined on a circle. So you kind of think of a function defined on a circle. Now we're going to look at, and I realize you guys have learned a little bit about complex numbers. So if I have a complex plane here, I got 1, 2, 3, I, 2I, 3I. Here's 1, 2, 3, I, 2I. Here's negative. So above, when we were looking at f of x is equal to sine x, we're looking at a function that takes the real numbers and maps it to a real number. So I put in a number like 0, and I get 0 out because sine of 0 is 0. If I put in pi over 2 maps to 1. So I can use 2 dimensions. I can use 2 dimensions to graphically represent a function of one variable. But if I deal with complex numbers, I need 2 dimensions just to graphically show a complex number. So if I want to, let's look at f of z is equal to z squared. F of z is equal to z squared. So z is typically used as a variable for a complex number. So we got z is equal to x plus iy. That's just by convention. We use z to represent a complex number. So if someone says, graphically show me what happens with f of z equals z squared, I can't show it on 2 dimensions because it's 2 dimensions already here, this complex plane. So I have to map from the complex plane to the complex plane. So let's take I, for instance. What does I map to? So if f takes z to z squared, then it takes I to I squared, which equals -1. So it takes this I and maps this point to this point here. Moreover, I could take the numbers in the upper quadrant. If I take the first quadrant, the points in the first quadrant are going to map to the upper half plane. So I could say that f of z is equal to z squared maps the first quadrant to the upper half plane. So this is the beginnings of the study of complex analysis. So I think somebody's teaching complex analysis. Is it Dr. K?
Yeah.
Dr. K, okay. So now here's the interesting thing is if I talk about functions of a complex variable, I can have functions that are doubly periodic. They can have two periods. You know, so I can create, for instance, let's look at here 1 and I. And I can create a function that has two periods, 1 and I. I could say that f of 1 plus z is equal to f of z, and f of I plus z is equal to f of z. Just like for sine, I could say that if f of x is equal to sine x, that f of x plus 2 pi is equal to f of x. So in a function of one variable, I could have a period, a single period, and then I could think of this as a function of on a circle. But here, if I look at a function that has two periods, I have a fundamental domain that if I know what happens in this function on this domain, I know what happens for the function for the whole complex plane. All I need is that fundamental domain. Just like here, above, all I needed to know for this trig function is everything from 0 to 2 pi. So this is called the fundamental domain. Fundamental domain. And so the fundamental domain is a parallelogram. The fundamental domain is a parallelogram. So I'm going to come over here, we're going to visually see what happens here. See, if I have a fundamental domain that's a parallelogram, everything, the values of the function along opposite sides are the same. The value of the function here is the same as on the opposite side. Oops. Okay. So, and if I glue these opposite sides together, I get a torus. And then we're talking about functions that are defined on a torus. So an elliptic function, this is super duper simple, elliptic function is a doubly periodic function of a complex variable. So I can think of elliptic function as a doubly periodic function of a complex variable. Now there's a formal definition, I think it's over here. This is from Reed College. If you're taking the class at Reed College, it's saying elliptic functions are doubly periodic meromorphic functions. But we won't worry about meromorphic, what that means. But if you're interested, meromorphic is basically a holomorphic function. A meromorphic function is a function that's holomorphic except for the poles, except for a bunch of isolated points. Those are the things in the denominator that cause the denominator to be 0. And holomorphic is just the fancy term for differentiable. It's just considered to be a function that's differentiable. So basically, but for the purposes of our class, if you just simply say that an elliptic function is a doubly periodic function of a complex variable, that's good enough for me. And we can think of it as being defined on so here, this is what's happening here. We have the function, it's a function of a complex variable, which is going to have two periods. So a fundamental domain is a parallelogram. I'm going to glue the opposite sides together, and so I end up with a function on a torus. So elliptic functions are functions defined on a torus, just like trig functions like sine and cosine are functions defined on a circle. And you know what's interesting is that I can parameterize a circle with sine and cosine, right? I can say, I could on a circle, I could write x is equal to, I could cosine t, y is equal to sine t, and then that parameterizes a circle. If I grab all x and y, where I let t vary, it parameterizes a circle. So it turns out that one of the most basic elliptic functions is called the Weierstrass P function, the Weierstrass P functions, and it turns out that the Weierstrass P function and its derivative parameterize an elliptic curve. It parameterizes elliptic curves, and these are functions that can be thought of as defined on a torus. And so we call these functions of genus 1 because there's one hole in there. The donut has one hole. There's other surfaces that have two holes that we call those functions of genus 2, and so forth. So this is really a super duper simplified version about what elliptic functions are. But please don't run out and tell other people that Dr. Wang told us that elliptic function is a doubly periodic complex function, because that's not quite right. There's some other conditions that you put on there, but what you really want to realize is that for singly periodic functions as one period, you can define that on a line segment, and a line segment topologically is the same as a circle. So I can talk about functions on a circle. Elliptic function are functions of a complex variable, so they're defined on the complex plane. They can have up to 2 periods, and when you have 2 periods, you have a fundamental domain on there. So let's fill in the blanks. Oops, I'm just gonna borrow this really fast here. I'm gonna read over here. So, what is considered the greatest math problem of all time for Maslow's theorem? State the assertion is that x to the n plus y to the n equals z to the n has no positive integer solutions where n is greater than 2. Right? What is a Pythagorean triple? Pythagorean triple is a triplet of positive integer solutions to x squared plus y squared is equal to z squared. So a Pythagorean triple is a triplet of numbers, a triplet of positive integers that satisfy x squared plus y squared is equal to z squared. So some examples are 3, 4, 5, 5, 12, 13. This one I'm going to, Dow-Fantine equations just means that you want to solve the equations in the integers. That's what Dow-Fantus was a Greek mathematician that studied how to solve problems with answers in integers. You saw some of these in elementary schools where it says there's a bunch of goats and chickens in a farm, and there's a total number of legs, and you know that goats have 4 legs and chickens have 2 legs, and you figure out there has to be an integer number of chickens and goats, and you can solve these problems using the fact that the answers are integers. So the study of Dow-Fantine equations, or the study of equations that involve integers as the answer. What does the complex function f of z is equal to z squared map the first quadrant of the complex plane to? It maps the first quadrant to the upper half plane. You don't necessarily have to know that. I mean, I'm just, so for the quiz, I'm just going to ask you to state from Mott's last theorem. Oh yeah, who solved for Mott's last theorem is Andrew Wiles. Andrew Wiles. I'll send out an email summarizing all this for y'all. An elliptic function can be thought of as a function of a complex variable defined on a parallelogram, which is topologically equivalent to a torus. So torus, donut, okay? And therefore, an elliptic function can be thought of as a function of a torus. Similarly, the trigonometric functions sine and cosine can be thought of functions as on a circle. And don't worry about the last piece about I'm going to show you how to find the greatest common factor of 2 positive integers without knowing the prime factorization. So, if you were part of the math counts competition, I coached one of the top math counts students back when I was in the Dallas area, and he knew a lot of little tricks. Like everything I showed him, he knew this, that, other thing, but he did not know how to find the greatest common factor of 2 numbers. So just to kind of summarize over here, let me make sure, and then we're going to wrap things up, because we're supposed to end at 2:20, but that clock is a little bit fast there. So an elliptic function can be thought of as being defined on a parallelogram. Which is topologically equivalent to a torus. Torus is like So we can kind of think of it, the fundamental domain of an elliptic function is a parallelogram, I should probably say. So that means that once I know what happens there, like I know everything about a trig function if I know what happens from 0 to 2 pi, if the period is 2 pi. So the fundamental domain of an elliptic function is a parallelogram. So the analog of the trig functions, for now complex numbers, you have a plane. You're defining a function on a plane rather than a function on a line. So when we do functions of a single variable, I'm mapping from a real number, I map it to a real number. I could show that on 2 dimensions because I'm showing the function. Now I can't do that for a complex function because I'm mapping from a plane to a plane. So there's no easy way to visualize that. And then remember a Pythagorean triple. Pythagorean triple is a triplet of positive integers such that positive integers x, y, z, such that x squared plus y squared is equal to z squared. So what are some examples? Oops, sorry. Oh, sorry. See, the thing is the only way I can advance it is pressing that little thing that says, okay, so I won't advance. So, examples are 3, 4, 5, 5, 12, 13, 8, 15, 17. There's an infinite number of Pythagorean triples. So these are right triangles. So here you got 3, 4, 5 right triangle. Okay. You have been a super duper wonderful audience. I'm going to do a follow-up email just telling you what's going to be, the quiz is just going to be stating Fermat's last theorem, who solved Fermat's last theorem, what's a Pythagorean triple, give me some examples. My goal for giving the quiz is just give you opportunities to get a perfect score and do well in the class. Okay.